So for number 1, my starting value, it doesn't ask for this one, but anyway, is 6,000. So you're starting with 6,000 of something. Then I'm going to ask myself, is this growth or decay, and by what percent? So, so if this number right here is bigger than 1, then that means you have growth because you're multiplying it by a number bigger than 1, which is going to make the value larger, right? So we would have growth here and spell. And what percentage is that growth going to be by? I've already used this example, so it's going to be 5%. Okay. Now, a systematic way of getting that right every time, for your growth or decay rate, you're adding 1 or subtracting 1 from it. So if you take this B value, 1.05, and subtract 1, you'll get 0.05, and then change that to a percent by moving that decimal 2 places, and that'll give you your value right there. I think that's particularly helpful on problems like number 2, where we have 3 to the x, because this always confuses me. I get my percents messed up here. So, this one's tricky too. What's the starting value for this? Is it 1 or 3? Okay. This number right here, the 3, is being raised to the x power, so it has to be your b. So 3 is going to be my b. I don't have an a there, but I could put a 1 right here, and it would not change the value of anything, right? That would still work. So the starting value here, Gabby is correct, is 1. But it looks like it should be 3, because it looks like you should have something there, right? So the starting value, if you're missing the starting value is 1. Okay? So if I want to know about growth here, what's happening is I'm multiplying by 3 each time. So that means I'm tripling whatever is there. So if I start off with 1, I'll triple it, I'll get 3. I'll triple it again, I'll get 9, and so on. That's what my values will look like. What percent growth is tripling? It's 200. This is always a little bit confusing for me. So that's why I do the same thing I did over here on this one. 3 minus the 1 that had been added to get the b value is going to give us 2. And then that is a decimal, even though it doesn't look like a decimal. So I have to move that decimal 2 places to make it a percent, and I get 200%. So it's 200% growth. So, and this may also help a little bit if you are doubling something. That is 100% growth. If it's triple, that is 200% growth. If you are quadrupling something, that's 300% growth. That sometimes doesn't seem right to me. Sometimes it seems like doubling should be like 50 or 200, or 100 doesn't seem right. But 100 is correct because it's you got 100% of what you already had and then 100% more, which doubles it there. Okay, questions so far? All right, for 3, what's my starting value? 700. Okay, is this growth or decay? Decay, because that b value is below 1. So you can do the same thing for this. Do 0.98, subtract 1. When you do 0.98 minus 1, you're going to get negative 0.02. And this negative right here is telling you that you've got decay. And then your rate, we're going to move that decimal 2 places, we'll get 2%. So we've got 2% decay. If you kind of think of it, your starting point's always 100%. If you got 0.98 here, you got 98%, you took 2% away from it. Right? Okay. Questions so far? Lyndon, what's my starting value going to be for number 4? Very good. All right, and what is the, or first of all, do we have growth or decay? Decay. What percentage? It's 50. This one you can kind of mess up on and still get it right, because the way that you should be doing it is 1/2 minus 1 gives you -1/2, which is going to be, that tells you it's decay. It's 0.5. Move your decimal 2 places, you get 50%. But if you look at it this way, it's also 0.5 to the x. So you can kind of think of it wrong and just use your b as your decay, but 50% is the only time that's actually going to get you the right answer. Because over here, if you did that, you would say it's 98% decay, and that would be wrong, right? It's only 2% decay. Okay, questions? All right, let's look at doing some problems with this. Okay, so you invest $600 in an account earning 5% APR compounded annually. How much money will be in the account in 5 years? Okay, so we're going to use that formula. We'll have y equals starting value here is 600. My b value needs to be 1 plus my rate as a decimal, which is 0.5. I'm sorry, no it's not. What is it? 0.05. Testing in there. So 0.05, which gives me 1.05. And then your x value here is always some sort of time. Because it's compounded annually, and this is years, the x right here is your number of years, so you just have to put a 5 there. Okay, so you're just going to type this into your calculator. Grab mine. And we've got 6,000 times 1.05 to the 5th gives us 7,657. I'm going to round this to 2 decimal places since we're talking about money. So $7,657.69. So this is for interest that is compounded annually. A lot of times when you go to a bank to set up something like a savings account or something, your interest is not compounded annually. It might be compounded more frequently than that. It might be monthly, it might be daily. It just depends on what bank you're at. I want to say mine is monthly, but I don't know if that's right or not. I should look into that. I should know that about my account. But I mean, I don't think there's a lot of options. You just kind of get what you get, so I haven't really thought about it. I should look at it as a math teacher. So compounded monthly is going to be different because when you see APR there, that is annual percentage rates. Okay. So when you see APR in a problem, or sometimes it will say 5% per year, That is your annual rate. That is how your percentage that you get every year. But if you're compounding monthly, they are not going to give you the annual rate every month. If you find a bank that will do that, put all of your money there. You're going to be really rich really quick. But you won't find it. So what we have to do for this is, since we're compounding monthly, that means that I must adjust rate and time to monthly, or months here. So if I've got 5% per year, I need to know what percentage that is going to be per month, because I need my formula to be in months, right? So this is a really simple calculation, particularly if you have a calculator available, and it will be available to you. How many months are in a year? 12. So if I've got 5% per year, I can just take my 5% and divide it by 12. And that will give me 0.416 repeating. Now, you do need to keep in mind this is a percent. You may prefer, instead, like if this is 0.05, this percent is 0.05. This is 0.00416 repeating whenever you change it to a decimal, because this is still a percent. What you may want to do is go ahead and use your decimal. So instead of doing it like I've done here, do 0.05 and divide it by 12. And that way you have a decimal right here. Or, to change a percent to a decimal, you're just moving that decimal place 2 places and filling in with zeros. So instead of using the 0.05, I need to use the 0.00416 repeating, because that is my monthly rate, and I'm compounding monthly. Also, for my time was given in years, 5 years. But I need my time now to be in months. Okay? So, 6 years, how many months is that? 60. Right? So, like, on Grown Ups, whenever the mama is still nursing the 4-year-old, she says that he's 48 months old. This makes it sound younger, right? So we're switching, just multiply by 12 right here. For this, we've got our equation for compounded monthly. Principal value is still the same. It's still 6,000. But we've adjusted our percent, so we're going to have 1.00416 repeating. And instead of using 5 for x, we're going to have 60 right here. And so we'll type that in. And to do repeating decimals on this calculator, just put a bunch of 6s. It'll be close enough, because it's eventually going to get where the calculator can't be more precise than that. So there's no specific number. 10 is probably plenty. A few extra don't hurt. Just put a bunch of 6s there. And we get 7,700.15. So $7,700.15. So you can see you get like what, about 43 extra dollars just by compounding monthly. So if you are ever at a bank and you have options, most of the time they just tell you we compound this monthly. The more frequently that interest is compounded, the better, because they're adding that interest back to your principal more often. So you should see that the more often you're compounding, you should see higher numbers there. But you will not see huge differences. So for example, what I see students do a lot wrong a lot of times is they do this, 6,000 times 1.05 to the 60th power. They don't adjust their rate. They did remember to adjust their months. If you do that, you're getting $112,000 and $112,075.11. That's why I said if you can find a bank that will give you the yearly rate every month, do it, because that would be a great deal. But that doesn't happen in real life, right? So that would be way too big. The other thing that students do sometimes is maybe forget to change the months as well. So you got to adjust both time and your rate. Okay, so let's do another one like this, and it's a little bit of a different problem. Okay, if Alfredo invests his money in an account that gets 4.8% APR, compounded quarterly, how long will it take his money to double? What's missing here? How much money does Alfredo have? We don't know, right? So what I want you guys to do, I need everybody to make up an amount of money that Alfredo has. I'm going to say that Alfredo has $648. You are not allowed to use 648. You must use a different number. So come up with an amount of money that you think Alfredo has. You are going to use your number for Alfredo. I'm sure I created this problem when Alfredo Sixtos was in my class. So Alfredo has $648. It is compounded quarterly, but this interest rate is annual. And occasionally I forget to put annual interest with it. I forget to put APR. They pretty much always give you your annual rate for this. So unless you see otherwise, assume it's annual. So if I've got 4.8% per year, I really prefer to do it this way, 0.048 per year. Go ahead and do the decimal. How many quarters are going to be in a year? Quarter. Four. Right, so if I take that 0.048 and I divide it by 4, I'm going to get 0.012. Right. Yeah. Okay, so my B value here is going to be 1.012. Okay. This exponent is my time. So right now, I don't know how long it takes. That's my question, right? I don't know how long it takes. So X is what I'm looking for, but I must remember over here, I'm going to put myself a note. X is number of quarters. Because since this is interest compounded quarterly, my time is in quarter of a year, not whole year. All right, so I want to know how long it takes this to double. This also is going to show you why this is in this section. Like, why are we doing this again? And what have we learned that is going to help us do this better now? Although Math 3, you still do this. So if I want to know how long it takes this money to double, you should have a different number than 648. I want to know how long it will take for his money to double. So I'm going to have 648, and I'm going to double it, and that is $12.96 for me. So I want to know when Y is going to equal $12.96. I want you to do the same thing, but use your numbers. So you should have a different number than 648, and you should double it to get this number that goes over here. Okay, the reason that this exponential stuff is in this unit is because what are we going to have to use to solve this? We got to use the log to solve it. So to solve it, I would divide by 648 first for mine. You're going to have a different number. That is going to give me 2 equals 1.012 to the x power. Okay, you guys divide your numbers as well. What did you guys get with your numbers? You should have gotten 2, even though your numbers are different than mine. So no matter what number you started with, you should have the same equation right now. So if you see a problem like this that looks like it's missing information, and it is missing information, you can just make it up because it's not going to matter in this case. So everybody should be working from the same thing now. How do I solve this? Okay, we can rewrite, or I like to think of it as an inverse. So to get rid of 1.012 to the power, I need to do log base 1.012 on both sides. So my answer, almost answer, ends up being log of 1.012 of 2. And to type that into the calculator, I would do log of 2 divided by log of 1.012. And I get 58. So x equals 58.108. Okay. What's that measured in? 58.108 what? Quarters. Okay. So if I ask you how old you are, and you tell me that you are 58.108 quarters of a year old, I will think that you are crazy, right? Because who would tell their age in quarters of a year, right? So, I probably don't want this to be my answer because quarters of a year doesn't really help me a lot on what I want. So what would I do to change this back to just years? We got to divide by 4 because there's 4 quarters every year. So we're going to divide this by 4. And we got 14.527 years. Which is pretty cool. It takes your money the same amount of time to double, no matter how much money you have. So if you put $1 in this account and leave it there for 14.527 years, you would have $2 at the end of that time. So you have doubled your money. Your increase percentage-wise is the same as somebody who put $1 million in the account, waited 14.572 years, and then got $2 million out. It takes the same amount of time to double. This is why they tell you have to have money to make money. In lots of ways, that is true. Your money's going to double in the same amount of time. But if you only put $1 in there, you only get $2 out. If you put $1 million in there, you get $2 million out. You've made $1 million versus making $1. So if you have money to invest and do it wisely, I guess you make poor investments, but then you get a larger, it's the same proportion of returns, but the number itself is way bigger. So I think this is pretty cool. So I never, when I would do, I picked 648 here just to prove a point. I usually would pick easy numbers. I usually would use 1 and 2, or 100 and 200, or 1,000 and 2,000. I would usually use easy numbers. I picked 648 to prove a point that it doesn't matter what number you pick. You can choose anything there. All right, let's see. I'm gonna give you one more thing here. If you look this up, if you look up compound interest on like Khan Academy or something, they're gonna give you a formula. So I'm gonna give it to you, and if you like the formula, that is fine. You can use it. I like to think of it as switching from years to months, and because I can remember that, and no matter what I'm dealing with, it makes sense to me. And I don't have to remember a new formula. So I like that because I don't like remembering new formulas. So that's the way I teach it because I feel like it will last longer. Like if you understand what's happening, that you'll actually be able to do it longer. However, there is just a straight formula that you can use. So that formula is P times 1 plus, how do they usually do that? R over N to the N times T. You may see this formula with different variables, but in this variable, P is your principal value. R is your rate as a decimal. N is the number of times compounded per year, and T is your time in years. If you think about it, that's what we did. We took our rate when it was months, we divided it by 12. That was the number of times compounded per year. And then we took our years and multiplied it by 12. So we did N times T here to get that. So that is exactly what we did. It's just in formula form. So if you prefer a formula, this is fine. It will not be given to you, so you have to have it memorized if you're going to use it that way. I like to reason through things better, but there's some people are really good at like memorizing formulas and just using a bunch of them, but it's not my preference. Also, let's go ahead and do this because it may end up being an issue. If you see semi-annually, that is 2 times per year. Okay. Quarterly, obviously, I've already done that one 4 times per year. Then, let's see, you're probably not going to see anything again till monthly is 12 times per year. Here's the ones I get questions about on the quiz, so there could be one of these on the quiz. Weekly. As juniors and seniors, you should know this, but I have found not everybody does. 52 times per year. And daily. How many days in a year? 365. If you want to get super technical, I guess there's like a quarter with the leap year, but don't use that. If you see something that's yearly, use 365.
There's 360 degrees in this earth. 365 days in a year.
The best thing is he does all that stuff to mess with people, and sometimes it works so good. Now, he wasn't the one that did this. We used to have this custodian named Tom, and he's passed away now. He was an older man. He'd come in and clean our rooms, and if it was a hot day outside, he'd say, "Phew, I think there is something to that global warming. It sure is hot outside." And then if it was a cold day, he'd come in, "I don't think they know what they're talking about with that global warming. Look how cold it is today." And it was always a comment like that, and it would drive Miss McComb crazy. which, I mean, I understand that, like, the temperature on a single day is not a good basis for, denying or claiming that global warming is, but you know, I also understood that Mr. Tom was an older man that probably, you know, didn't know or care about that or really want to be educated on it. So I just went, oh, I think you're right. Went along, but Miss McCollum would drive her crazy. Who? Oh, he might have, yeah. Coach Wood understands, definitely, that the global warming temperature for the day is, those two are not like good arguments, but he loves to throw it out there anyway. He loves to throw out things like flat earth theory, and he's messing with people all the time, which I like about him. Even though I'm not usually his target, so yeah, it's good. I don't know if I'd like it as much if I was his. Okay, all right, we're going to do this one more thing. Actually, let me see. We don't need to do all of these problems for you to be able to do the assignments, but I need to pick them wisely. I have such a good problem. But we're going to do 5. Okay, let's do 5 and then we'll skip to 1 or 2 of the others over here. All right, so continuous growth or decay. I'm probably not going to get time to explain it tomorrow because tomorrow we're on a short schedule. So take my word for it today. But I'm going to try to go back and explain to you where E comes from because I think it's cool to understand that because E shows up in all kinds of other places. But A equals PE to the RT is our formula that we can use for continuous growth or decay. Because as we were looking at our list over here, you know, semi-annually, quarterly, monthly, weekly, daily, you could keep going, compounded every hour, every minute, every second. I promise I won't ask you to do those. The most I might ask you is for daily there. And if I do daily, I'll probably have like 3.65 or something that'll divide fairly easily as your rate. Daily is the most you really need to know. But we could do hourly, every minute, every second, every nanosecond. Eventually, continuously would mean it's just like compounded all the time, right? That's what you would eventually get to. So I will go through and try to like kind of explain where E comes from a little bit more. But if you're going to have continuous growth or decay, you want to use this formula. Sometimes it can be a little bit hard to understand which one you're going to use, whether you're going to use the ones we were already using or use continuous. And there's some cases where you could use either one. I try to make sure I always put the word continuously in the problem if I'm wanting you to use this formula. So if you see that something grows continuously or decays continuously, go with this formula, okay? So P is your principal. E is just the value we've been using for E, 2.71828, and so on. R is your rate. Again, here your rate as a decimal here. And let's put us a note right here. Do not add 1 or subtract 1, right? Because this is not the same as the B value. You're just putting your rate there. So if the rate is 5%, you put 0.05 there. And T is your time. So, and depending on the problem, that might be years, it might be months, it might be hours, days, whatever. If it is interest, it goes with whatever your interest rate is given to you. So if you have an annual interest rate, you would plug in years for your time. If you have a monthly interest rate, you would plug in months for your time. It's usually going to be years. So, Walter just got a job as a high school chemistry teacher. His first year, he lives with his parents, and he saves $20,000. He puts the money in an account that earns 6.75% interest compounded continuously. If he leaves the money in the account without making any deposits or withdrawals, how much money will be in the account when he retires 29 years from now? So, If we're going to use the formula for this, y equals PE to the RT, principal here is 20,000. And then, if you can do this, this is such a great idea. Because we're going to see here in a second. So, 20,000 E to the R, which is going to be 0.0675, times our time, which is going to be 29. You can see I forgot to put APR with that rate. If you see something that doesn't tell you how often the rate is compounded, if it doesn't say per year or APR or something, assume I meant yearly, because I just forget to leave it off the problem sometimes. On the quiz and test, I'll try to be really sure that I put that on there. All right, so if we type this in, we got 20,000 times E to the 0.0675 times 29, and we get $141,632.02. So if you can say, like, if you have a long time, if you can put money in your retirement early and it has longer to sit there, it really like blows up. If you only put it in here for 5 years, it's going to be a lot smaller. Like if this was 5. But sometimes that's hard to do whenever you just got out of school and you finally have some money and you just want to spend it. Because, I mean, some of you guys may not be broke in college, but I was broke in college. And I just, when I like actually got paid real job money, I felt like I was so rich. I just want to spend some of my money. That's not the best long-term plan, but same. So, he wouldn't have even had to start making meth and selling it on the streets here if this particular teacher was Walter White from Breaking Bad. So, if only he had done this. Actually, he ended up with way more money than that. But, you got Miss White, the old calculus teacher that retired several years ago. Her husband's name is Walter. He ran for county commissioner in Dobson. There were signs everywhere that said Walter White for county commissioner. Or not county, city commissioner or whatever. So, I was wondering if there would be anybody wanting to take those signs. Okay. Alright, so we're going to do just we need to do a decay problem, and I didn't put any of those on that first one. It's on the second. So if you go to that second page that I gave you. I need to go through and streamline these notes because it feels like we're skipping a lot, but I didn't. I knew we weren't going to have time for all of this. So, oh wait, I picked the wrong thing. Sorry. Here we go. Oh, this one. Those are already filled in. Come on. There's at least a decay problem. Okay. So increases. Okay, let's do 7 first. We're going to do 7, then we might do one more, but we might not have time. All right, so a new car cost $43,000. The value of the car depreciates at a rate of 11% per year. How long will it take for the car to be worth less than half of its initial cost? Except for crazy times like right now, when there's been a shortage and used cars cost almost as much as new cars, and like normally a car is going to depreciate unless we're talking like some classic car that you just have sitting in the garage to rub on every once in a while. You know, if you actually drive it, it is going to depreciate. Your cars usually never gain value. There's some weird times going on right now, but usually cars never gain value. So, and we got to be coming down off of that surely by now, because it's like prices of used stuff went crazy. So for this, what we're going to do is we got y equals our initial cost is $43,000, and for our b value for 11% per year, we got to do 1 minus 0.11, which is going to give us 0.89. So you can think of this, it's not the percent that the car loses, but the percent of value that it keeps that you want there, right? So if it lost 11% of its value, it kept 89% of its value. That's the number that goes right here. And that number should be less than 1 there. And then we're going to put an X right here. We don't know what that is. Now, this problem, they didn't give us a time, but they did tell us less than half of the initial cost. So we're going to take that half right there, and we're going to plug that in over here. So half of 43,000 is going to be 21,500. And then we can solve this using the way we've learned to solve log equations. So we can do 43,000. That's going to give me 1/2 equals 0.89 to the x power. Okay. How do I get rid of that 0.89? Log with a base of 0.89. So my x is going to be log base 0.89 of 0.5. What's going on over there? Log of 0.5 divided by log of 0.89. And we get 5.948. Correct. And that is because our percentage was per year, which is normally what you see. But if it was losing 11% per hour or something, then our answer would be in hours. That for a car wouldn't make sense. But okay, so we did not get to do a half-life problem. So on your homework, I'm going to have you guys get the half-life problem. If it was not for beta kids, I might just go ahead and have you guys take, like, I might push the quiz back to Friday, but beta's going to be gone, which is half of it. So what I'm going to do instead is I'm going to take the half-life problems off of the quiz. So I will not put any half-life problems on the quiz. Let me tell you which ones it is here that you do not have to do. We will still go back and do a couple half-life problems later once beta kids are back, but I just won't put them on the quiz. So, well, they're not. Actually, I don't know if I have half-life problems on here, except for, don't do the last one. 12, I think, is my only half-life problem. Hello? Sure can. Thanks. Alright. Lolly, Miss Mullis needs to see you. of this is on Canvas, so check your work as you go if you get stuck. And I do have smart breakfast in the morning.